Ever wondered why some AI models solve complex problems faster than others? Or why bigger isn't always better when it comes to AI efficiency? Today, we're diving into a groundbreaking study from Carnegie Mellon University that's redefining how we measure AI performance, and it's turning long-held assumptions on their head. Let's start with the basics: test time scaling. This isn't just about raw processing speed, it's about how models adapt during inference. Techniques like long chains of thought or sampling multiple answers improve reasoning, but they come at a cost. Traditional research has focused on computational power, ignoring a critical factor: memory access. Here's the kicker: memory access. How quickly a model retrieves information is the real bottleneck. Think of it like a traffic jam. Even with a powerful engine, gridlock slows you down. This insight led researchers to develop the Kinetics scaling law, a framework that balances computation and memory. Their findings: smaller models, once hailed as efficient, aren't as effective as we thought. Once models hit tilde 14 billion parameters, they start outperforming smaller counterparts, especially when using advanced techniques like long chains of thought. But why? The answer lies in attention, the mechanism AI uses to focus on relevant information. Traditional models spread their spotlight everywhere, which is slow and costly. Enter sparse attention, a smarter approach where the spotlight hits only critical spots. This isn't theory. Sparse attention models generate way more text with the same resources. Imagine writing a novel, but only using a fraction of your keyboard. Efficient, right? In tests, these models scored over 60 points higher on problem-solving tasks in low-cost settings, and still beat others in high-stakes scenarios. And here's the twist: as we invest more computing power, sparse attention becomes even more critical. It's like upgrading from a bicycle to a rocket ship. Efficiency scales exponentially. Researchers built a simple version of this technique, achieving up to 26 times faster performance on GPUs. But this is just part of the story. Techniques like chain-of-thought tuning let models adjust their thinking based on task complexity. For example, a model might use a quick process for simple questions or a detailed, step-by-step approach for complex ones, saving time while maintaining accuracy. Processing long texts is computationally heavy. Traditional models pay attention to every word, like a detective checking every clue. Sparse attention changes that. Methods like asymmetric indexing or block sparse attention let models focus only on relevant parts, slashing computation. It's like skimming a book instead of reading every page. Then there's speculative decoding. Think of it as a writer testing multiple essay versions simultaneously. Techniques like Specinfer and Magic Deck generate answers in parallel, cutting response times without sacrificing quality. What if you don't have a huge computer? Innovations like Skeleton of Thought and Quest use smart shortcuts to generate answers faster, while ShadowKV and FlexGen optimize memory for longer texts. Open-source tools like Snowflake Arctic are making these advances accessible to all. Why does this matter? These techniques break the speed versus quality trade-off. By making AI more efficient, we unlock practical uses, from faster medical diagnoses to smarter educational tools. And the best part? Many methods are open source, letting the whole community build on them. Next time you chat with an AI, remember, behind the scenes, researchers are fine-tuning invisible tricks to make those conversations smoother, smarter, and more efficient. Thanks for watching, stay curious, and let's keep exploring the mind-bending world of AI together.